All right, hey everyone. Yes, I'm Kevin Scaldeferri. I work at New Relic, where I'm a principal engineer and an architect for our distributed database systems and query engines. Contrary to what you may have heard in some previous talks, we do not just run open source components on other computers for you. We are building our own things. It's very cool if that's something that you would like to do. We are hiring, so you can talk to me later. Anyways. I am also sort of an unabashed math geek. So that leads to writing talk titles like, you can't spell monitoring without monoid. So I'm going to have to explain exactly what that means, what a monoid is, but I want to avoid sort of a common trap that people fall into with these sorts of talks about abstract math concepts, which is to go straight into the definitions without sort of providing some context and some motivation. So we're going to spend the first part of this talk doing that. So I have a confession that may be a little bit heretical in this crowd, but I don't really like metric time series. So I'm sure that there are a bunch of people who are now saying, Kevin, what's not to like about metric time series? They're so simple. You just have timestamps and numbers, and what could be easier? And I will agree with you that they are easy. But I'm also going to argue that they're not simple. So if you've never seen Rich Hickey's talks about this distinction between simple and easy, I highly recommend going and looking them up. Sort of without spending a whole talk on this distinction, I just want to say we sort of know when we're writing systems that if we're going to write clean, well-factored, maintainable code, that's not actually generally easy. When we do easy things, we take shortcuts, we intertwine multiple concepts in ways that complicate our ability to think about them. So I'd like to tell you a story. A few months ago, we were having a production incident. We had multiple systems that were misbehaving. We had a lot of teams who had gotten paged. And we had some of our best incident responders were in the ER trying to figure out the common thread between all of them. And all of a sudden, one of them says, I've got it. Look at this chart. The whole time that this incident has been going on, CPU is going up and to the right. The foobar DB is foobarred. Page the database team. So they paged the database team. A few minutes later, someone joins the Slack channel. They show him the smoking gun. And he says, nope, 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 nope. That's totally normal because that metric, that's not a gauge. It's an accumulative counter. It always goes up and to the right. This chart, which is labeled CPU usage, is not really displaying CPU usage. It's displaying uptime. Totally useless to us in this scenario. I find charts doing the same thing all over the place. So if I'm writing an application, I'm deploying it out onto our container fabric. I need to decide how much CPU I want to reserve for that. If I don't reserve enough, my app's going to get throttled. It's not going to perform well. That's bad. If I'm never getting throttled at all, then I'm probably wasting CPU. That's not awesome either. So I want to monitor how much CPU throttling I'm getting in my application. But this is the sort of data that comes out of the monitoring systems off of the OS. And the person who made this dashboard, they were kind enough to make it clear this is the total lifetime throttled time. So I know what I'm looking at here. I've been given a hint that this is an accumulator, not a gauge, but it's still sort of useless. I can't correlate this to other things that are going on in my application. I have 3 instances which have totally different amounts of throttled time. Are they really behaving differently? Did they just get restarted at different times? And you can transform this and get the deltas, and that works to an extent, but it does limit what you can do with this sort of data. Okay, so we have counters, gauges, our other major type of metric time series. Let's talk about them for a little bit. So a couple weeks ago, I was traveling. I live in Portland. Was going up to Seattle for a couple of days. Any given day, you can take about 10 flights, go from Portland to Seattle. That takes about 40 minutes. And then there's, 1,000 cars, I don't know. They're making the drive, and that takes you 3.5 hours. So let me ask a question. How long does it take to get from Portland to Seattle on average? So we could do the math like this, and it tells us that the average time for that trip is just 2 minutes less than 3.5 hours. But I mean, if you think about that, that doesn't feel quite right. The explanation is that each one of those planes has about 120 people on it. Each one of those cars has one, maybe two in it. And once we take that into account, we can do the average correctly, and it brings the average time per person down to about 2 hours. It's kind of in the middle of the two modes of travel. All right, what does this have to do with metrics? Well, okay, let's imagine instead we're measuring our average response time on an app that's deployed out to 3 hosts. So 2 of them are pretty fast. They're responding in 10 milliseconds, more or less. Another one is much slower. We want to know what's our average response time overall. So if I add those 3 numbers up, divide by 3, I'll get 34 milliseconds. Is that the average response time that we're seeing for all of our users? It's probably not. Why isn't it? So you have a load balancer that's sitting in front of these 3 hosts. It notices that one of them's not doing well. It routes fewer requests to that host. So that means that taking a naive average of these averages is going to give you the wrong answer. Now, no doubt, someone in this audience is going to say, well, you shouldn't even be looking at average response times. Really, percentiles are where it's at. So we also report percentiles as gauges frequently. This is sort of an abbreviated version of what would come out of a Dropwizard app from their metrics. Includes a number of p-values in there. So I can go to, and I can grab this off of all of my hosts. But now what am I going to do with that? Okay, so going back to our SLI talk yesterday, we know that we want to base those on what our users are actually seeing. And our users don't care about the P99 for a single host. They care about the P99 for the entire application. So what am I going to do with this per host data? I think Liz already sort of told us earlier. I'm going to say it again. I'm going to just use a shameless appeal to authority here. So this is Gil 10. He's a guy who knows a lot about measuring performance, particularly about measuring outlier performance. He wrote this blog post a couple years back. It says, title is "You Can't Average Percentiles, period." You just, you can't. Or you can, but the answer that you get is wrong. So it doesn't actually tell you whether you're meeting that SLO that you set for your application. There's just no mathematically correct way to combine those individual P90, P99 values from multiple instances into a single value. Okay, one more sort of gauge value I'm going to talk about is unique counts. Because unique counts are actually really something that businesses care about a lot. How many unique users are coming to the site? How many unique users have tried a new feature? This is a very high value data point, and it's a problem to try and track it. Because the issue is that, say, over the course of a week, we track the number of unique users for each day. We want to know now, okay, how many unique users did we have for the entire week? Well, you can't determine that from this data that we have here. The best that we can do is we can put some bounds on it. In this case, we know it has to be at least 20. 20 was the day that had the largest number of unique values. But we could have been getting totally different users throughout the entire week, in which case it would be the sum. So it's somewhere in this range between 20 and 111, which is not a really great estimate if you're going to go back to the business and try to give them an answer to this question. So this is all a little bit depressing. There's lots of things which we would like to measure, and we have a hard time doing them in ways that actually give us correct answers. What can we do about this? We can use some math. So let's finally talk about monoids and how they can help us out of this mess. Okay, so what is a monoid? This is a fairly typical definition. A monoid is an algebraic structure with a single associative binary operation and an identity element. So let's unpack that. The first term we had in there was algebraic structure. This is honestly like a little bit of a noise word. But basically let's think of this in programmer speak as like a data type or a class, a data structure. Pretty vague category. An associative binary operation is just something like addition, basically like addition on our numbers, normal numbers. And then an identity element is just something that acts like 0 does for normal addition. So if I translate that into something like an interface definition that we would write in our programs, it looks like this. A monoid is something that takes a type T and it augments it with a way to add 2 T's and also defines a special 0 element of T. So those operators, they need to satisfy some additional rules. They're a little bit outside of the type system. But I put those in the comments here. So the addition needs to satisfy this associative property, which basically says when you have a string of things that you're adding together, it really doesn't matter how you group them with parentheses. You'll get the same answer no matter what. And then the 0 element is just something that if you add it to something, it doesn't change it. Right now we're using the terminology and we're using the symbols for addition, but this is a much broader concept. So, for example, multiplication is a monoid, but there we call it multiply and 1. String and list concatenation is another simple example, and then we call it append and empty. Okay, so that's a pretty simple concept as far as these things go. In fact, it's so simple that you might be asking, how is this actually useful to us at all? So I'm going to walk through what it is the simple concept unlocks and how it gets us out of some of the problems that we were running into when we were taking the easy route. So there are 3 main things which I'm going to explain that monoids are getting us. The first one, the one that's most apparent from the definition, is that monoids are what allow us to do aggregation both in time and across the dimensions of our high cardinality data. So, we like to sample metrics, pretty frequently these days, maybe every 5 or 10 seconds. In some systems, you might want a second or faster. And that resolution is extremely valuable for tactical purposes when you're trying to fix a problem in the moment. But it's also really expensive and generally unnecessary to store all that data if you want to do longer-term strategic analyses. So what that means is that we need the ability to be able to roll up those measurements over longer timescales. So maybe we're only going to store 1 data point per hour or per day for things that we want to do analyses over, on the scale of months or years. And the additive nature of the monoid is what lets us do that. And that associative requirement, the thing that says you can put parentheses wherever you want, means that we know we get the same answer if we've done this sort of pre-aggregation. But then we also have all of these, this high cardinality dimensions that we're gathering on all of our data now, right? Because we don't deploy just a single instance of a database anymore or of a service, right? We deploy many redundant instances. We're not, well, most of us are still deploying, the remnants of a monolith, but for the most part, we're trying to move to microservices. So we have lots of services that we're deploying. We're going into multiple AZs, multiple geographic regions. You might be using multiple hardware classes or EC2 types. And there's far more that's useful, and it's, this is the detail that's really valuable when you're trying to track down a problem, to be able to, slice and dice that across any of these dimensions. But we also need to be able to answer those broader questions, those higher level questions about the systems in aggregate. We need to, actually track those user-facing SLOs and those metrics which are, valuable for the business, not just for operations. So, we need to be able to go ahead and collapse down those dimensions to answer those questions, and also, again, to reduce storage costs, because, a year from now, you probably don't care about container ID anymore. That's too much detail. So, in practice, what does making a shift over to using monoidal structures for this sort of data look like? So the first thing is that we have to get away from accumulative counters, and we need to replace them with delta counters. And of course, at a low level, those CPU stats that we're getting, or those network stats, like, we're going to get accumulators, but as quickly as possible after we gather that, we need to convert them into more useful measurements, things that say something like this: the 12 requests to this endpoint were received by this host during this time interval. And what we also need to be told is that summing them up is the right thing to do. Because again, like I said a moment ago, monoid is both a data type and a combining operation together. And that same raw data type, we could have multiple monoid operations that are associated with it. And we need to know, like, what's the right one for a particular data point, that particular double or long that we've collected, what's the right thing to do with it? For example, we have lots of gauges that might be measuring the min or max value of something. So it doesn't make any sense to sum or to average those numbers. Instead, we need to take the max of all of our maxes. We need to take the min of all of our mins. That's often sort of implicitly encoded in the name of a metric, but it would be much nicer if that was actually something that was explicit in the telemetry data that we're collecting. So we want our monitoring to actually tell us directly that this metric should be aggregated using the max function, for example. Okay, the second thing that we get from using monoids is composability. So what does that mean exactly? It means that if we have monoids on two monoids on simple data types, we can turn that into a monoid on the pair of the data types. So for a concrete example, let's go back to talking about average response times. So we had a service that was deployed out to 3 hosts, and each one independently has an average response time. What are we going to do in order to be able to get the average for the entire system? Well, so we actually have to be tracking 2 numbers for each host. We need to be tracking the total time that we've spent servicing requests and the total number of requests that we got for that host. So on their own, that's a sum monoid over those floats, the time that we spent, and a sum monoid over integers for the counts. But when you pair them together, you get the average monoid. And now we can do the aggregation across all 3 hosts. We can sum the times, we sum the counts, and we do the division to get the correct value, which is very different than what we got if we just did the average of the average. Again, we do this implicitly with the names that we attach to metrics, but we could do this better by actually being explicit about that pairing. And this is a simple example, right? But yesterday, Brian Lau was showing us a Prometheus histogram. So that histogram structure, that's also a monoid. And that's why it's a useful thing for our services to be emitting, because we can take that and we can go ahead and we can group it, we can aggregate it, and we're doing the right thing with it. Now, unfortunately, personal opinion here, I think the Prometheus line format is sort of an abomination. If we've talked about, hey, we should use structured JSON logs. We should do the same thing with those metrics and not shoehorn them into this ugly format. That's my little rant today. Okay, third thing that we're going to get. is that monoids, they give us a structure which allows us to design approximate algorithms which are still mathematically sound. So, our unique count example, we go back to that. As we said, those counts for each day, they're not sufficient to let us calculate the unique users for the whole week. We need to do something else. And what to do, is not at all obvious. But, there are researchers who have worked on this problem for a number of years, and there's sort of a line of papers that more or less culminates in this one, which introduced a data structure called hyperlog-log. And I'm not going to make any attempt to explain how this works, but you can Google it and find descriptions later. The thing that is sort of important to know for our purposes right now is that using this algorithm, you can track an estimate of unique counts for billions of items in about 700 bytes. And you can then combine those estimates together and you'll get an accurate estimate for longer time periods or aggregated across dimensional space. And 700 bytes, that's a lot compared to the 8 bytes that we were keeping for the typical longs and double metric data points. But on the other hand, there's probably not nearly as many unique counts that you want to be tracking on your system. And they're usually fairly high value data points. So this can be a reasonable trade-off to use that space. And as a result, we're seeing in various storage systems like Postgres and Redis, you have first-class support for hyperlog-log values. A few of the monitoring tools out there are also using this. Now, what about percentiles? So the good news about percentiles is that there are lots of ways to approximate them monoidally. But the bad news is also that there's lots of ways to approximate them monoidally. So this is not a complete list. This is just, I think, some of the most well-known approaches to this problem. And again, I'm not going to make any attempt to actually explain exactly what any of these are or how they work. But you can look them up. Some of them are taking statistical approaches to deriving features of a distribution. Some of them are basically just fancy high-resolution histograms. There are others that take a sampling approach to the problem. And they're all making these trade-offs in this sort of space of speed, size, and accuracy of the algorithm. And this is still a very active area of research. We've already heard once today about DD's sketch. So that's the last one here. This is a new algorithm that was just published a couple months ago. Actually, one of the authors is speaking later this afternoon, but on a completely different topic. And so the difficulty that we're facing here is that unlike unique counts, where we've sort of decided that there's one algorithm that hits the sweet spot, when it comes to percentiles, there's really no agreement about what the best thing to use is. We haven't settled on anything. Everyone is making different choices. And this really presents a challenge for gathering metrics across all of our systems in a consistent manner. Okay, so this is usually the point where some people's heads are spinning, so we're done with the math. You get a happy dog photo. This is, my wife sends me photos of our dog while I'm away. This, I got this yesterday, made me smile. Hopefully makes you smile. And okay, now we will wrap up a little bit. So let's summarize what we've talked about. So metric time series. They've been the easy, dominant paradigm for monitoring data over the last decade or so. But they increasingly present challenges in today's environments. Because they have such a limited data model, the consumers of the data need significant out-of-band context to interpret it. And if you don't have that context, the numbers can be misleading and they can cause unnecessary confusion. I've sort of harped on accumulative counters as one of the worst offenders here, but they're by no means the only one. Because we have this data that doesn't tell us what it means, it's easy to make a mistake and apply mathematical functions to it that are nonsensical. And also, in many cases, these simple time series, they don't give us a way to aggregate over long time periods or across our high-dimensional cardinality in mathematically sound ways. Monoids provide a simple framework which allows us to build mathematically sound monitoring systems. In this case, the type of the data tells us what calculations are actually meaningful. So, we've already started to see proposals like the open census spec, that allows us to specify what the units are on a particular metric, or also to add a human readable description onto it. So that's great, but I would also like to see us go a little bit further and add a machine interpretable data type onto those metrics so we know how to do this sort of thing automatically and we can guide people away from making mistakes. Let's see. The ability to aggregate arbitrarily here means that we can collect raw data at the timescales and details that we need, but avoid it being prohibitively expensive in the long run. And although the individual monoids may be simple, we can compose them to do more complicated things. And those monoid laws, they teach us how to design the algorithms that we need to do approximate calculations over massive data sets. So, challenges that the industry needs to address, in my opinion. I think we need to move beyond just our sort of simple single value metric time series and accept that some of these composite data types are really a necessity, whether that's for the most basic examples like averages, whether it's for your histograms, or whether more sophisticated examples. We need to see sort of wider adoption of hyperlog-log for doing unique count aggregation. And then finally, I think the biggest challenge that we're facing here is this consensus around quantile estimation. I think this is something that we're going to have to confront as we're gathering telemetry data from more and more diverse sources that are all doing things in different ways. We need to sort of move towards more of a consensus about the right way to collect data that we can use to do quantiles. Okay, that's everything. Thank you all. It's my contact information again. Let's see here. Looks like I maybe have one more minute. I could take, take a question or two. I don't want to stand in the way of lunch too much, but hard to see here. All right, we got one up in the balcony. Yes, so the question was how monoids are used at New Relic. They are used sort of everywhere. I mean, it is at some level, core mathematical concept to how all of our systems work and how we're able to collect, high cardinality event data and then perform computations over that. Even our traditional APM metrics are also based on a monoidal framework. We don't always use that language, but it is core to how we actually do computation, how we collect our data, how we aggregate it, how we process queries on it. Anything else? No? Okay, well, in that case, thank you. If you want to come and talk to me later, love to chat. And I'll let you all get to lunch.